Okay. Hi, everyone. I'll introduce Professor Sitan and then hand it over to him for the talk. So today I have the pleasure of introducing one of our most eminent speakers in this seminar series. So Sitan Chen is a professor of computer science at Harvard, where he's the member of the Theory of Computation group, the ML Foundation group, as well as the Harvard Quantum Initiative. He works on designing algorithms with provable guarantees for fundamental problems in all kinds of problems, but mostly focusing on generative modeling, deep learning, and quantum information. He was previously an NSF postdoc at UC Berkeley, where he worked under guidance of Professor Prasad Raghavendra. He received his PhD in EECS from MIT, where he was advised by Ankur Moitra. There he received the MIT Presidential Fellowship as well as a PD Soros Fellowship. Prior to this, he was a math undergrad and a CS undergrad at Harvard, where he had the opportunity to work with the eminent Salil Wadan as well as Leslie Valiant. So without further ado, I'll hand it to Sitan for the talk.
Great. Yeah, thanks, Rahul, for the introduction. Very excited to talk at the seminar. Thank you so much for the invitation. So I'll be talking about some joint work with Yuanzhi Li. These are some of our, based on some of our recent work on understanding, learnability for transformers. Okay, so please feel free to stop me at any point in the middle of the talk if you have any questions. All right, so I guess just at a very high level, of course, as we all know, transformers are this architecture that's been the workhorse behind all these state-of-the-art approaches to natural language processing and vision, a la things like GPT. As we know, with like many things in deep learning theory, this is something that's widely successful in practice, but poorly understood from a theoretical perspective. And so in this talk, I'm going to tell you about a very clean mathematical sandbox where we can hope to rigorously prove things about the learnability of these functions. So I'll tell you about some of the first provable guarantees in this direction, and I hope to mention various open problems by the end. Okay, I should mention that this work comes in kind of the wake of a long line of theory work on understanding a more traditional architecture, which is this feed-forward architecture. I should emphasize that there are still many mathematical mysteries that remain for even in that setting. But today's talk, I hope to kind of look outwards and kind of see to what extent the theory for learning transformers, this more modern architecture, compares to this broader body of work that came before. And as kind of a spoiler for what I'll talk about, the answer seems to be that the theory diverges quite significantly. At least based on the results I'll tell you about, it seems like the mathematical tools that are needed for understanding transformers could shape out to be very different from the one needed for understanding feed-forward architectures. Okay, so let me begin with some basic preliminaries so everyone's on the same page in terms of definitions, and then I'll turn to what we show. Okay. So let's begin by just making sure everyone is on the same page with notation regarding the attention mechanism. So in this talk, we'll think of single head attention as the following. So it's a sequence-to-sequence function that takes as input a k by d matrix and outputs a k by d matrix. Here you think of k as the length of your context. So it's the number of tokens. And d is sort of the dimension of the sort of embedding of your text. Okay, so each row of this input sequence x you can think of as corresponding to some word in a sentence of length k. Okay, so that's our input sequence x. So this function takes as input x and spits out some other sequence of k tokens. And it's parameterized by two objects. I'm just going to give them names so it's easy to refer to them in the rest of the talk, but these names aren't super important. So I'm going to refer to theta as the attention matrix. This is some d by d matrix that specifies some inner product in d-dimensional space. Theta can be arbitrary and need not be symmetric. And then there's also the projection matrix. Again, a d by d matrix, it need not be a projector in the linear algebraic sense. It's just some name that we're giving it. Okay, so the sequence-to-sequence function f is defined as follows. So we look at the following matrix. We look at x theta x transpose. Okay, so this is some k by k matrix. And roughly speaking, you can think of it as like every entry of x theta x transpose corresponds to maybe the correlation between a particular pair of tokens as specified by the inner product theta. Okay, so it's some kind of almost like a gram matrix, but for this particular inner product, and we pass this through this softmax function. So the softmax function operates on a row-wise level. Okay, so the softmax of x theta x transpose will be some other k by k matrix, where every row has entry summing to 1. And then we further multiply this row stochastic matrix by xw. Okay, so just to parse what's going on in maybe like the ith row of this output. If I look at the ith row, then the thing that goes inside the softmax, recall, that's just a bunch of inner products. So it's essentially the inner product of the ith token, xi, so that's the ith row of x, with all rows of x. Okay, so I look at the inner product of xi with x1 relative to this inner product theta, xi inner product x2 with respect to theta, etc. Okay. And then I pass this through a softmax. So a softmax simply exponentiates each of the entries and divides by the sum in order to produce a probability vector. And that probability vector will sort of tell me, how am I going to sort of recombine the different tokens in the input sequence, right? So it specifies some convex combination of the original rows of x. So when I multiply x by softmax, I just get some, linear combination of the rows, and then I apply some linear transformation to that linear combination. So that's yes.
Two quick questions at this point, just to understand the setup. So in this set of parameters, I guess theta and w are learned. And
that's right. So yeah, so I haven't told you yet the learning setting, but yes. We're going to ultimately think of theta and w as something in this, some ground truth parameters that we don't know, and our goal is to produce, estimates for these parameters. But for now, let's just think of them as, some parameters defining some function class.
And the second question was, what is w projecting onto? Like when you call it a projection matrix, projection some space or?
Yeah, so again, it's just a name, but in practice, what will happen is W you can think of as maybe like potentially a matrix of rank less than D. So if there's some factorization of W into I don't know, two components A and B, then you're kind of thinking of the component A as really like you're projecting onto the kind of like the column span of A. But this kind of this aspect of the problem won't be super relevant for us. I'm just using this terminology for convenience. Yep.
Thank you.
Yep. Great questions. Okay, yeah. So just to hammer home the kind of what this mechanism is doing, right? So softmax is kind of converting this into a probability vector and then recombining the inputs, the tokens x, and then applying some linear transformation. That's essentially what every row of the function is doing. And you can kind of think of the softmax as I mean, if you've seen blog posts about transformers, this is really the picture that's going on. The softmax is telling you to what extent, for instance, each particular token, in this case, the ith token is maybe the word to what extent it tends to all the other tokens in the sequence. And so if you have maybe like a train model and you look at some attention layer in the middle of this model, you might find that the attention mechanism is having the ith token point most of the mass towards the word dog. Okay, so that's just some way of visualizing what's going on with the softmax. Okay, but in any case, this is some mathematical object we can define. Let's now move to the main focus of this talk, which is not single head attention but multi-head attention. Right, so multi-head attention is nothing more than a sum of single head attentions. Okay, so it's still a sequence-to-sequence function, and it takes as parameters now multiple attention matrices and multiple projection matrices, theta 1 through theta m, w1 through wm. Okay, And as the notation suggests, it's just a sum of the corresponding single head attentions given by each pair theta I wi. It still takes as input a k by d sequence and outputs as k by d sequence. Okay, so let me clarify, in case you've seen transformers in other contexts, the notation is actually quite different from what people often use in practice. The reason I'm condensing this notation in this fashion is that it's actually, a generalization of the family of functions that people, try to learn in practice. But the exact parameterization of the function that people use in practice is often of this form. So this is a lot to parse. So I'm not going to go into details about this notation, but at a high level, what people like to do is instead of taking just a matrix theta I, they like factorizing theta I into some matrix that corresponds to producing kind of like so-called query values for the inputs. So it's denoted by Q, and then some matrix that corresponds to producing sort of keys for the input. So that's why this is called K. So you can think of this WQ, WK as really just some factorization for the attention, what we're calling the attention matrix theta. Similarly, this projection matrix, it's actually just some combination of this matrix that's sitting on the outside, which is producing so-called values for the input. That's why this is called V, and then applying some global linear transformation. So all I want to say in this slide is that this kind of formulation is kind of a special case. It's essentially the low-rank case of this parameterization that we saw on this slide. Okay, and this factorization. Oh, sorry.
Just wanted to clarify that we are looking here at a single transformer block, and if there are multiple transformer blocks, you might have X as an output of a previous block.
That's right. So what we're doing in this talk is focusing on one layer. In fact, we're not even considering any kind of layer normalization or MLP, just the multi-head attention layer. Okay. Great. Yeah. So this particular parameterization is relevant if you want to maybe train a student network in practice. But for us, we think of this function as just something that nature is giving us, and the particular parameterization in terms of a factorization, of course, that's not going to be uniquely specified. And for us, we ultimately just care about the product of these kinds of matrices. Okay, so that's why we'll focus purely on this parameterization in this talk. But again, assume it sort of subsumes what you would encounter in a typical ML blog post on transformers. Okay, so great. So now let me tell you a bit about what's known on the theoretical side for transformers. So I would say the vast majority of existing works, too many to list on one slide, so I'll only kind of subsample the earliest ones, have focused on the representational power of this function class. Okay, so they're really saying, there exists, settings of the parameters of a transformer that allow it to maybe implement a particular class of functions, maybe more efficiently than some other architecture. Okay, so they're really focusing on the existence of weights for the transformer, rather than focusing on something like whether or not you could actually find those weights using gradient descent. Okay, so this is these are purely existential results. There are also some works on sort of the statistical side of things. That kind of bounds the number of samples you would need to learn a transformer. But again, these are only information theoretic in nature. They don't really say why you could do such a thing in polynomial time. They really just say, if I run something like empirical risk minimization, how many samples do I need before I get a certain level of error? Okay, so these kinds of works follow kind of in some sense from existing techniques in the statistical learning theory literature based on things like covering number bounds. There's another kind of orthogonal line of work to ours based on interpreting kind of the evaluation of transformers as really running some discretization of a sort of neural ODE. And so these works kind of understand, try to understand this ODE from a dynamical systems perspective. This is not really related to the learning aspect that we'll consider, but there's a lot of interesting math that arises in these series of works. So the ones that will be most relevant to our talk are the works on actually training, trying to understand training dynamics for these small transformers. And I'll say that essentially all existing works really focus on training dynamics for a single attention head, and specifically for very specific simple synthetic tasks. Okay, so they pose various simple toy models for data and try to show that if I train a single attention head using gradient descent, they can solve these tasks. I should emphasize that these are settings where the learning task itself is in some sense trivial. So if you're happy with giving any algorithm for these tasks, there's not really much to do. Really, the hard part is understanding why, if you train a single attention head with gradient descent, they can actually solve these tasks. Okay, so this will turn out to be a bit different from the focus of this work. Let me finally mention that there are, to my knowledge, maybe like 2 works on, multi-head attention layer. There are, by the way, many other works on understanding attention in the context of linear attention, where there's no softmax. So I'm omitting those from the slide just because the setting is a little different. There are, however, a lot of works, or a couple of works on understanding multi-head attention layer in regimes where the dynamics kind of look linear. So there's this paper by Fu, Guo, Bai, and Mei that considers kind of this like random features perspective on multi-head attention, where you essentially think of the theta matrices as frozen at the outset, and you only train the W matrices. Okay, so this is ultimately a linear problem, and they prove various bounds on this. Then there's also this work by Diora, Gaderi, Taheri, and Athrapalides that studies train dynamics in kind of like an NTK regime. So this is still kind of within some sort of linearized setting. So in this talk, we're going to kind of escape from this linearized setting and really just consider the full kind of non-convex problem. So here's I guess the backdrop for today's talk. We're going to study learnability under just the following sort of 2 constraints. We're going to ask, can you efficiently learn this function class that I've defined if all you assume is, 1, the data comes from a somewhat nice distribution? So here, when we think of nice, we're kind of putting on our TCS hats and considering distributions like maybe the Gaussian distribution or maybe the uniform distribution over the hypercube, something that doesn't have too much crazy structure in it that might make it hard to come up with an end-to-end analysis. And then secondly, we're asking, we're going to ignore aspects of whether or not this function class is sufficiently expressive. We're going to assume actually the labels that we get in our training set are perfectly explained by some multi-head attention layer, in the sense that there's some ground truth function that's generating our data. Our goal is just to be able to find that ground truth function or approximate it. So I'll define this formally in the next slide, but this is kind of the general setup we'll consider. I should emphasize that.
Hi, I have a question.
Yes.
Yeah. So in the settings in the previous slide that you considered, so is one of the assumptions that can be made, for example, that X comes from, so you say X comes from this K by D matrix, but can you assume things like it's low rank because X essentially is coming from a set of discrete discrete parameters?
So yeah, so the previous works, they often make pretty specific kind of toy assumptions, like maybe you think of like for instance, one example could be you define some sort of like transition matrix on over a universe of tokens, and then each row of X might just be like a one hot vector corresponding to one of the tokens, and then you sample the rows of X using this transition matrix, and maybe the one hot token, these one hot encodings of these tokens then get passed through some fixed linear function that corresponds to kind of a dictionary from tokens to vectors. So yeah, fairly structured things. We in this talk we'll think of K. I'll get into the details of this, but K will ultimately be bounded relative to the dimension, and so we're naturally in this kind of low rank setting. it's of course interesting to try to extend beyond that setting. But yeah, I'll talk about the caveats in a bit. Those are the kind of assumptions that are used previously. So I should just emphasize that unlike these existing settings I mentioned in the previous slide, here it's not clear at all if we have any provable algorithm for learning, let alone an end-to-end analysis of gradient descent. So for us, the gold standard will be to develop any kind of end-to-end provable guarantee for this learning problem. Okay, so here's formally the setting. So this is something that this is kind of like a general perspective that the computational learning theory literature has taken before for other kinds of function classes. This is maybe sometimes called realizable packed learning. So the premise is you get the following. You get various sequence-to-sequence pairs, x1, y1 to xn, yn. Here I'm using the same subscript notation as before, but just to avoid confusion, here each xi is actually a k by d matrix. So it's not a particular row of some matrix, it's actually an entire sequence of tokens. And each yi is the corresponding output sequence under some function f. Okay. And what we're promised is that each of the xi's is sampled IID from some nice distribution d that I'll specify in a bit. Okay. And so all we assume is that there is some fixed but unknown function f that's explaining all of our data. So yi will be equal to f of xi for all I. So what is the algorithmic goal? The goal is just to produce some estimate, f hat. It could be some arbitrary function if you want to do improper learning, or in our case, we can actually do proper learning. So we're going to ask for another multi-head attention layer f hat, which approximates the unknown multi-head attention layer f well in some average case sense. So concretely, we want to show that with high probability over the randomness of the samples, our training set, and high probability over the randomness potentially in the algorithm, the expected squared distance between our prediction f of x for a fresh sample x from the distribution, the ground truth prediction f of x, the distance between that and our prediction f hat of x in Frobenius norm squared, we want that to be small. So this is kind of, things are all, the labels are matrix valued, so this is why we need a Frobenius norm. But ultimately, you can think of this as just some notion of square loss for this task. Okay.
Professor, there's a question on chat from Sachin here. He asks, how much are the assumptions that you made valid in real-world problems?
Yeah, I mean, this is the usual question that people ask. Yeah, it's a great question. The answer is currently we're still studying a fairly toy setting where we're not making any kinds of, for instance, structural assumptions on the underlying distribution. In fact, in this work, we're going to focus on just the uniform distribution. The other question is, to what extent are things nice and realizable? This is, for a single layer, it might be, pretty hard to encounter data that's perfectly, fit by a single multi-head attention layer. But I should mention that there's some interesting work by Ronan Eldon and my co-author Yanzu Lee showing that even if you just work with, a single attention layer, but you compose it with maybe one feed-forward layer, so just one hidden layer of let's say ReLUs with linearities, this is already enough to generate coherent English. Okay, so actually, if you can go slightly beyond this theory and get something that involves both a multi-head attention layer and a multi-layer perceptron with just a two-layer multi-layer perceptron, then you already start running into situations where this assumption can capture fairly rich distributions. Okay, so I would say one of the caveats is that the underlying distribution has to be uniform over the hypercube. But as we'll see, the kinds of features of this uniform distribution that we exploit are actually things that I suspect are much more general purpose. But this is kind of the starting point for most of deep learning theory at this point. You can't really hope to get learning guarantees over kind of general distribution families. And it's really like a big open question, even in the kind of traditional feed-forward setting, what are the right distributional assumptions under which you can hope to get provable guarantees? I hope to show in maybe like the next half hour that the ways in which we're exploiting this distributional assumption are actually fairly robust, and hopefully should extend to even richer input distributions. Okay, so but this is sort of what we can work with and show at the moment in the theory. Okay, but it's a great question.
So effectively on this side, you're seeing that the pairs xi, yi are learnable, and x is coming from quite a rich function, probability distribution like uniform -1, 1,
That's right.
which is already quite expressive. Okay.
That's right. That's right. Okay, and I'll say the ways in which we use this distributional assumption shortly, but yeah, this is what we'll work with. So I should mention that our techniques also handle kind of the Gaussian case implicitly, because the proofs will ultimately use certain central limit theorem like tools that compare these two distributions. In fact, the Gaussian case thus is actually strictly easier, but we'll focus on the uniform distribution. At the outset of the project, we really wanted to consider some input distribution that has kind of a discrete flavor. To kind of mimic the discrete structure of the distribution over real world tokens, which you can think of as just I take some discrete distribution over strings and then maybe apply some embedding on top of that so that they're real vectors. But ultimately, this distribution that we're trying to capture is discrete in nature, and so the uniform distribution is kind of the simplest possible distribution that would try to mimic this discrete structure. Of course, the dream would be to extend this to more structured distributions than just the uniform one, but this is what we can show. Great. Okay, so this is the setup. Let me tell you a bit about what we prove. But before I tell you about our results, I want to kind of contextualize this within the broader landscape of deep learning theory, at least from a sort of TCS perspective. So like I mentioned, there's been a ton of work on learning feed-forward networks, rather than transformers, and almost all of these works focus on essentially one hidden layer networks. So these are what I was calling maybe like a two-layer MLP in the previous slide. So this function, it's not super important for this talk what exactly this function is, but okay, it's some notion of taking linear projections of the input given by these weight vectors wi, mapping them through some nonlinearity sigma, and then linearly recombining all these different linearities using some coefficients lambda I. Okay, so it's some scalar valued function that takes as input a vector x and outputs some number given by this linear combination. All of the work that kind of goes outside of this linearized regime where you can use kernel methods will focus on the Gaussian input distribution, almost exclusively. And the kinds of guarantees that are known here are kind of the following flavor. So for worst case feed-forward networks, it turns out that the best thing that we can currently prove kind of scales exponentially in the size of the network. So in this case, the number of nonlinearities, sigma of wi in a product x. And so I won't go into details about these results, but we can show certain things that scale as d to the maybe poly m or maybe even d to the m. And some of this theory can actually go beyond depth 2, but ultimately we have to incur some exponential dependence on the size, in some cases for good reasons in terms of cryptographic lower bounds. Okay, so I won't go into details about these results, but this is sort of what's known. What I do want to maybe focus a bit more on is the extent to which these results utilize certain features of the problem. So I'll say that essentially all of the existing guarantees essentially exploit some subset of the following aspects. So first, recall that these one hidden layer networks ultimately depend on projections of the input x to the directions w1 through wm. So if you think of the size as maybe smaller than the dimension, if it's bigger than the dimension, then a lot of things are sort of open. But if we think of m as smaller than the dimension, then this function is ultimately only depending on the projection of x of the input to the subspace spanned by these vectors w1 through wm. Right, so this makes f what's called a multi-index model. It only depends on a bounded dimensional projection of the input. Right, so this kind of low dimensional structure is quite useful in a lot of these analyses. Some of these other works also, focus on, some of the, these works also exploit things like the Gaussian input distribution has this, uniquely defined property that, it's a product distribution and is rotationally invariant. Okay, this is very useful for instance, exploiting this first bullet point, this low-dimensional structure. In fact, there are some simple algebraic tricks that allow you to extract out, directions which are orthogonal to the subspace spanned by W1 through Wm. Okay, so I won't go into the technical details, but this is kind of another nice feature of the problem that essentially all these works exploit. The last feature that these works exploit is this nice algebraic structure in the problem. So it turns out if you look at moments of this joint distribution between x and the label f of x, there are some simple ways to extract out low-rank tensors that depend on the parameters of the problem. Okay, so there exists certain statistics of the data that if you computed, they would exactly extract out some interesting algebraic objects that depend on the unknown parameters, and this is kind of the underlying trick behind essentially all of the existing works on feed-forward networks implicitly. Okay, so let's just kind of consider our setting now and ask, to what extent do any of these features map over to the transformer setting? And the sad truth is that essentially none of them do. Okay, so we can first ask, is this function class that we're considering a multi-index model? And the answer is, not necessarily, because we could even consider maybe parameters theta I, which are given by some full rank matrix. In that case, f of x you can't write as a function of just a bounded dimensional projection of the input. Okay, so the multi-index model, this low-dimensional structure goes out the window. We're already going beyond the Gaussian distribution by working with uniform over the hypercube. We're certainly going to leverage other properties of the Gaussian distribution, but we're not going to leverage this very brittle property that it's kind of product and rotational invariant. We're only going to preserve the productness and not this rotation invariance. Okay, and lastly, you can ask, can you extract out similar sorts of algebraic objects like these low-rank tensors from the feed-forward setting? And the answer is, at least to my knowledge, no. Right? Because these moments that we would have to exploit would involve taking expectation values of the softmax function. The softmax function, by definition, is you take an exponential and you divide it by a sum of exponentials. This, in general, once you have things in the denominator, this becomes sort of a nightmare to analyze. Okay, so at least to my knowledge, this moment structure seems very mysterious. I'll say a bit about how we can approximately exploit some very crude moment structure in a few slides, but at least the flavor of tensor-based methods that sort of dominated the feed-forward approach, the feed-forward setting, these kind of go out the window. Okay, so mostly bad news, and so I guess one general motivation for studying the multi-head attention setting is also just trying to identify what are structural properties of the problem that make efficient learning possible. Okay, because it seems like the structural properties of feed-forward networks really revolved around these three features, and none of these kind of carry over to our setting.
Okay. Professor Sitan, a quick question here. So there are properties of this function f, the form that you have considered, as well as properties of x coming from a hypercube. Yep. So hypercube obviously gives some sort of independence with orthogonal setting, right? Like a different form, of course, than the Gaussian one. But you're saying that this function f itself is complicated enough that doesn't allow the other features. But does it allow some features?
Yeah. So when I say orthogonality, I guess I mean that, okay, certainly it's true that because it's a product distribution, at least you have independence across coordinates by definition. So if I project in to disjoint sets of coordinates, I get a statistical independence of the input. But the key feature that's used for Gaussians is that this holds even if I project to arbitrary orthogonal subspaces. Okay, so I could take two linear forms that are just orthogonal. They need not be aligned with the coordinate basis, and I'm guaranteed that you have exact independence of those projections. In the Boolean case, this is only approximately true. certainly you can invoke various central limit theorem style things to say approximate analogs of this. We don't really have. We're going to use these central limit theorem tools, but we don't really have a need to understand, for instance, this kind of approximate rotation invariance structure because we're not able to leverage the multi-index model structure to begin with. And so we're going to use certain features that I'll tell you about. As a spoiler, we're ultimately going to use the fact that the Boolean hypercube has nice concentration properties, just like Gaussian. If I consider some linear projection of the input, it's going to concentrate well as a scalar variable. And we're also going to use the fact that if I look at dense linear projections of the input in some sense, they will also behave somewhat like Gaussian by the central limit theorem. But these kinds of tail bounds, actually, I'm not aware of existing methods for feed-forward networks in the Gaussian setting that only use tail bounds or anti-concentration. In fact, all of these works really are kind of leveraging this moment structure, which kind of all these three kind of features kind of play off of each other, and none of them kind of are able to only exploit the fact that the distribution, for instance, has Gaussian tails. They really need that they have Gaussian moments as well.
Okay, thank you.
Yeah, so I'll say a bit about what those properties are, but yeah, so there are certainly going to be features of the problem that we're going to exploit. Great, so let me tell you about our results. So we're going to work in some regime which, it's a regime in which we can prove results, but is by no means the sort of final word on this topic. So unfortunately, we're only going to be able to prove guarantees for a small number of heads, but I should emphasize that even the case of m equals 1, a single head, essentially nothing was known previously, okay? So we're going to consider m, which is at most roughly like logarithmic in the dimension. And unfortunately, we're going to only consider context lengths that are bounded relative to the dimension. Okay? So you can think of the context length as maybe some small polynomial power in the dimension. We'll see shortly why we need the context length k, the number of tokens, to be less than the dimension. Okay. So here's what we show. We show that for some non-degenerate family of multi-head attention layers, there is actually an algorithm that runs in time polynomial in the dimension, and fortunately exponential in the number of heads for pack learning in the setting. Okay, and so you might ask, like, why is there this exponential dependence, right? Why does this keep showing up both for the feed-forward setting, in these prior works, as well as for the transformer setting? And the answer is that if you're not going to make too many extra assumptions on the underlying function, if you just work with worst case multi-head attention layers, then even when the number of tokens is just 2, okay, so just 2-word sentences essentially, you already get this kind of lower bound in certain computational models. So under this so-called statistical query model, which I won't be able to define in today's talk, you can actually show that d to the m is, in some sense, the best you could hope for. Now, if you don't really believe statistical query lower bounds, you want to work with algorithms that might not be statistical query, you can still show that it would be too much to hope for a fully polynomial time guarantee, at least assuming certain cryptographic conjectures. Okay. So assuming some variant of the learning with errors problem that I won't get into the details of in today's talk. Okay. So this is sort of what we show. Yeah.
Most of the lower bounds that you mentioned even earlier were cryptographic lower bounds. In this area, is information theoretic lower bounds used at all, or?
Yeah, great question. So in the feed-forward setting, the lower bounds are, again, of these two flavors, either statistical query lower bounds or cryptographic lower bounds. For information theoretic lower bounds, the point is that because we're assuming that these labels are being generated by some teacher network, the number of parameters defining the teacher network is already polynomially large, right? Because I have m attention heads in this case. Each of the theta i's is a d by d matrix. Each of the wi's is a d by d matrix. So overall, I have maybe like 2m d squared parameters in total. And so information theoretically, there's actually no hardness, right? Because the number of parameters is small, in some sense, covering number of this function class will be bounded. And so I expect that if I just run a computationally inefficient algorithm like empirical risk minimization, then I would generalize in a polynomial number of samples. So really, this is like a very basic example of computational statistical gap, right? Because from a sample complexity perspective, there's no problem, but the challenge is really to produce a polynomial time algorithm. Yeah, great. Okay, so I will, I guess, I think I'm in the interest of time, because I want to get into the techniques. Let me just flash the slide to convey that there are, quite a lot of assumptions that we need to make, but I won't go into details about each of the assumptions. So there's a bit of fine print that I need to clarify before telling you, how we study this problem. So let me just show you, I guess, the three main parts of the fine print. There are some other assumptions that we need to make for technical reasons, but these are kind of the ones that are kind of essential to our analysis, or at least the first two. Okay, so we need to make the following assumptions about the attention matrices theta I. We need to assume that they're angularly separated, so they're incoherent in the sense that the cosine similarity between any pair of attention matrices is bounded by 1 over polylog d, poly m. All right, so m we're thinking of as logarithmic in d to begin with, so really you should think of this incoherence as something like 1 over polylog d. Okay, so in some sense, these attention matrices will be approximately orthogonal to each other, but the level of orthogonality is fairly benign, in the sense that if I took completely random attention matrices, just Gaussian attention matrices, for instance, the level of incoherence would be 1 over poly d. And here we're only asking for 1 over polylog d. Okay? So it's still some assumption we have to make, but somewhat more benign than you might expect. The other kind of main assumption we need to make is that the stable rank of these attention matrices is not too small. Okay, so the stable rank here is just the ratio between the squared Frobenius norm and the squared operator norm. So roughly speaking, you think of this like some continuous notion of rank, and we need to make sure that this is also lower bounded by k, m, and log d. Okay, but if, for instance, these theta a's were Gaussian, for instance, then certainly the stable rank is going to be of order d. We're able to tolerate something that's depending polylogarithmically on the dimension instead, but polynomially on the number of tokens. Okay, so the number of tokens should be some small, at most, some small polynomial power in the dimension for this to be non-vacuous. Okay, so these are sort of the two assumptions that we kind of heavily exploit in this work, and it's a great open question to try to remove these assumptions. We also need to make some technical assumption involving the diagonals of this matrix, specifically that the trace of any attention matrix is comparable to the Frobenius norm, whereas in the worst case, you can imagine the trace is only related up to a factor of root d. We assume that it's only bounded by a factor of root log k. Okay, this is ultimately, I think, purely an assumption we make for convenience. This is just to make sure that the diagonal entries of the softmax don't behave too differently from the off diagonals. But I suspect that this should be removable using, by working harder. Okay, so unfortunately, we have to make other assumptions that I won't get into the details of. Some assumptions that are specific to getting it to work in the Boolean case rather than the Gaussian case. These are just to ensure that certain central limit theorem like tools apply. But if you're happy with working with Gaussian, these are not necessary. And then finally, some assumption that again is for convenience. I think I strongly suspect this can be removed, but we don't, just because it takes a lot more work. We assume that the norms of the attention matrices are comparable up to some factor that we depend exponentially on. So we can think of this factor as maybe a constant factor. And we need to make sure that the norms are within some range, so that the softmax doesn't sort of degenerate. Okay, so these are some assumptions. I really want to emphasize that I think it's really the first two that are sort of necessary for our techniques, and the remaining ones are maybe ones that we make more out of the sake of convenience, or to handle Boolean inputs. Okay, but for instance, the Boolean input assumptions, like this non-arithmetic assumption, this even holds as long as you go into some, like, for instance, smooth analysis setup. Okay, so anyway, some fine print. I don't want to delve too much into the details, We make some similar assumptions on the projection matrices. They're actually a bit milder because we don't have to make any special assumptions to handle Booleanity. And further, the parameters for these other assumptions are a bit more mild. Okay, so that's the fine print. Just to be transparent about the guarantees. Let me now tell you about the algorithm and the analysis in the remaining time. Okay, so this algorithm, it's not going to be gradient descent, unfortunately. It's going to be some algorithm that we're actually able to get a theoretical handle on, but hopefully the analysis will reveal structural properties that are useful in an eventual analysis of gradient descent. So here's the algorithm. We're going to first obtain partial information about the function by crudely estimating the following object, namely the sum of the projection matrices Wi. Okay, so when you first see this, it might not be clear why this is a useful object to target, but this will be kind of essential to our approach. Once we have this estimate for the sum of the Wi's, the goal now is to estimate the following. So to get some more information about the parameters, specifically the attention matrix parameters, we're going to estimate the following convex body, which is the affine hull of the theta I. So it's the set of all convex combinations, or all linear combinations of the theta I's whose coefficients sum to 1. Okay, so it's larger than just the convex hull. It's you can allow negative coefficients in this combination. Okay, so once we have this affine hull, unfortunately, the level of error that we get access to it is too large. So we somehow need to refine this estimate. So then we go back to our original quantity of interest, the sum of the projection matrices, and we use the affine hull to somehow refine it. We then use our sum of projection matrices to further refine the affine hull. And at this point, the error in K is sufficiently small that we can hope to estimate the span of the vertices of this affine hull. And because we're thinking of M as small, this kind of restricts our problem now to a much smaller space, namely just the M-dimensional space spanned by the attention matrices. And now we can run some sort of brute force procedure to learn the function f over this small space. So I want to draw your attention mainly to the first 3 steps. These are sort of the hardest part of the analysis. The rest is more straightforward.
Sorry, Professor, just one question here. So to understand this algorithm, are you looping through estimates of Wi and theta I as you learn f, or is f only learned at the end after? Is there a loop running somewhere? Or?
There's no loop, yeah. So it's only a 2-stage refinement process. So you first crudely estimate them, and then you refine them once, and then that's enough to learn the function f.
And this assures you some epsilon closeness.
That's right. Yeah, great questions. Thanks.
I have a question.
Yes.
Yeah, so does the algorithm make sure that the initial estimates or the refined estimates satisfy the conditions that you have mentioned in the previous slides?
Are you asking, does the algorithm kind of certify whether these assumptions hold?
Yes. Yeah.
Yeah, no, this is, this is a feature of, so I think it could be, that's actually an interesting question. So if your function deviates from these assumptions, you could, there's all this interesting work, for instance, on like testable learning by Ronit Rubenfeld and Arsen Vassilian, Adam Klivans, and others, which says, I want a learning algorithm that's able to sort of both, learn, but also like certify that the data is actually sort of generated by the process that you're assuming. This is often harder, and it's kind of like a layer that people often put on top of existing learning algorithms. We haven't developed that yet. Yeah.
Okay. Yeah. Thanks.
Good question. Okay, so I'm kind of low on time, so let me tell you. I hope to tell you maybe briefly about steps 1 and 2. So let me tell you a bit about step 1, and then I do want to tell you why it's useful to know to be able to estimate the sum of the projection matrices. Okay. So here's the main claim about the sum of the Wi's. If you try to use gradient descent to learn this function, but you kind of maybe foolishly only train a single attention head to try to fit this multi-head attention layer, and you happen to initialize theta, your attention matrix parameter, to 0, and then take a single step of gradient descent with respect to just the standard loss, then the resulting estimate for the projection matrix will be close to the matrix of interest, the sum of the WIs. But it'll be close only up to an inverse polynomial in the stable rank in Frobenius norm. Okay, so more succinctly, this is essentially the term on the left-hand side is essentially the cross term that you get when you expand out the square loss. Okay, so this is really the term that we want to get a handle on, and it turns out it suffices to show that this approximates the sum of the projection matrices. Okay, so actually this gradient descent, it's really just for intuition for what this guarantee is really saying, but the main mathematical object we need to consider is really this. Okay, so you could just ignore gradient descent and just say, well, if I can estimate this matrix on the left-hand side by drawing samples, then I get an estimate for the thing I care about. Okay, so this is really the mathematical statement we want to prove. Okay, so just some notation, right? So X transpose, this is just the input sequence transpose. So it's a D by K matrix. The inner matrix is just the all ones matrix, K by K, and Y is this K by D output sequence. Okay, so it turns out by linearity it actually suffices to show that this holds for a single attention head. So for any fixed I, it suffices to show that this approximate equality holds. And then if I sum over all i's, then I just get the original inequality, equality. Okay, and so we see that there's a WI on both sides, so actually it suffices to show the statement when these are both identity. Okay, so this is really the mathematical statement that underlies this main step. Okay, so let's look at this. So here is some wrong intuition. Let's imagine that the inner softmax actually concentrated very well around its expectation, delta, well enough that we could even pretend, softmax for any choice of x is actually exactly equal to delta. So let's just approximate this by replacing this random matrix softmax of x theta x transpose by the expectation of that random matrix. And let's call that expectation delta. Okay, so I've replaced this kind of complicated, random object with just a deterministic object, and now the only randomness in the expectation is in the x's. Okay, so now this is something you can explicitly evaluate. So here we're using some basic information about correlations between entries of the input, and ultimately we get out the following expression. Okay, so this is some calculation one can do. And then, what is the trace inner product between the all ones matrix and delta? Well, delta is a row stochastic matrix. Every row, is a probability vector. It'll add to 1, and there are k rows. So this trace is just k. So k divided by k is just 1, and you end up with just the identity matrix as claimed. Right. So this is kind of the high-level intuition, but unfortunately, this intuition is broken. So it turns out that the inner softmax, it doesn't concentrate sufficiently well for you to just blindly run this argument. Here's like a basic example. Let's say like the theta matrix were actually sampled, let's say, from some Gaussian distribution, but the point is that the theta has fairly large Frobenius norm. Okay, because it is a fairly large norm matrix, the softmax essentially behaves like a hard max, and as a result, for a typical sample X, what you'll see is that the rows are actually almost one sparse. Right, so there's only one entry that's kind of non-trivial. Everything else is quite small. So even though the expected value of softmax might be some kind of dense matrix, right? So you see a lot of different colors just in the heat map. This is the expectation for the softmax, but in reality, for any typical choice of X, we're going to get sort of a one sparse. Every row is going to be one sparse. Okay, so we don't get the level of concentration we want. There's some technical work around this where instead of looking at just the full distribution over X, we kind of make the following argument. We say, well, if I look at a fixed substring of X and I look at its Hamming weight, I can look at the resulting conditional expectation on the softmax, conditioned on the Hamming weight being some particular value. And this conditional expectation, as a random variable in the Hamming weight, this actually turns out to concentrate fairly well for reasons that are rather technical to go into. But I think the main takeaway here is that just using concentration directly over the distribution over x's is not good enough. But if I slice the distribution appropriately, I can get the level of concentration that I need in order to implement the argument in the previous slide. Okay, but this part is fairly involved, and I won't be able to tell you about the details today. Okay, so that's the first stage. I want to emphasize that this has some resemblance to the method of moments, in that ultimately what we're saying is that we want to approximate some object of interest, namely the sum of the projection matrices, using an expectation value. But note that in the method of moments, usually this kind of relation is exact. You really want to say, if I could exactly estimate some expectation, it would exactly give me the object that I need, maybe some low-rank tensor in the parameters. Here, we're saying something very different. We're saying even if you had an infinite number of samples and could evaluate this expectation exactly, that object will only be approximately equal to the object I care about. And this approximation error is actually fundamental. It requires us to make various workarounds in order to really refine this approximation error to get something good. So this approximation error is not related to the sort of finite sample nature of estimating this expectation. It's really some fundamental approximation error that we can't get around directly. Okay, let me say briefly about the last step, because I realize I'm running out of time. Why is this projection matrix sum actually useful for our purposes? So let's say we were able to produce some estimate for W hat. So in this slide, I want to convince you that it actually gives us access to an approximation to the convex hull, or the affine hull of these theta matrices. And so let's run the following thought experiment. Let's imagine that we see some input x so that all of the attention patterns are related across the different heads, in the sense that if I look at the first row of the softmax output, they happen to be the same for all of the heads. Okay, so this is some very lucky event that we could hope for. Of course, they won't be exactly the same. There will be some level of approximation, but this is some lucky event that we can wait for by drawing enough samples. And in this case, let's say that the attention pattern in the first row, it's some probability vector, is some vector v. Now, if you look at the first row of the output and you pass through the logic, you'll see that because the softmax in each summand is the same, you can actually move it outside of the sum. Right? All of these share the same factor, v transpose. And so ultimately, the first row of y would then in that case be v transpose x times this sum of the projection matrices. Okay. And so this is why we really want to target the sum of projection matrices, because in this lucky event, you can actually write y as v transpose x times that sum. So if we can approximate this, now we have access to both x, we have access to y, and we have access to w hat. And now in order to check whether this lucky event happens, this is nothing more than a linear regression problem. Because y is the first row is ultimately a linear combination of these rows. Yeah, you can essentially certify whether or not you're in this lucky event where the softmax patterns are all the same by just running linear regression, turns out. Okay, and it turns out that once you are able to isolate this particular probability vector, then you can get out to linear constraints on theta by just looking at ratios between entries of this vector. This is just using properties of the softmax. Okay. So at this point, I'm going a little fast. So let me turn to the end. This is hopefully to convince you, why the sum of projection matrices comes up rather naturally. Okay, so let me conclude and maybe mention some open problems. Okay, so just as a kind of a general summary, hopefully this convinced you that at least realizable pack learning seems like a clean and tractable sandbox for understanding learnability of transformers. The main, I think, conceptual takeaway is that the properties that we're using about this problem are very different from what are used in the feed-forward setting. And I think it's actually a crucial difference from that setting that we're able to go beyond Gaussian inputs and work with something like the uniform distribution, which traditionally in learning theory one was only able to prove positive results about using, for instance, kernel methods, using things like polynomial regression. And instead, we're giving this kind of new mechanism for learning that goes beyond these kinds of kernel methods, but is still able to handle Booleanity. In particular, we don't use rotation invariance or delicate structure of the moments, only concentration and anti-concentration. I think the main open problem is we make a lot of assumptions on the underlying function, a lot of them actually just for technical convenience, but even under these assumptions, the proof is actually quite hairy. So it'd be great if one could actually remove any of these nicest assumptions or even impose new assumptions that are motivated by practice that could allow us to get fully polynomial time guarantees that avoid these cryptographic lower bounds. A more open-ended question is to what extent we can actually compose the theories for attention on the one hand and feed-forward networks on the other to get learnability even for transformer blocks, right? And it turns out that even with a single transformer block, like I alluded to earlier, you can already get very interesting generation. So this is from this Tiny Stories paper by Eldon and Lee. More generally, there are tons of other open questions related to, for instance, going beyond a single transformer block. Can you show, for instance, various cryptographic hardness results when you go beyond one layer that apply even in kind of non-worst case settings? This is something that's known in the feed-forward setting, but of course is very open in the non-feed forward setting. And of course, the ultimate goal of all of this literature is, at the end of the day, I want to understand why gradient descent works. This paper is really suggesting here are some nice structural features that the analysis could exploit. For instance, this nice property that the sum of the projection matrices you can learn with a single step of gradient descent, and furthermore, it's useful for then backing out constraints on the other parameters. Can these ultimately be leveraged in an analysis of more practical algorithms? So those are some general open directions that one can consider. I think in general this direction is kind of the wild west currently, and I think there's a lot of interesting theory waiting to be discovered. So thanks a lot for listening. Happy to take questions now.
Yeah, thanks, Professor Sitan. I think great talk throughout. I had a question going back to your algorithm.
Yes.
So can you move to that slide for a second?
Yeah, definitely. Yep.
Yeah. So what I see here is you're only estimating sum of WIs and also refining those estimates.
Yes.
But at some point, do you not need to? So to learn the function f, you would need the actual WI values, because if you estimate WI even exactly, let's say with error 0,
yes,
it's not going to be unique in the WIs.
Yes.
So to go back and get the exact f that satisfies that summation WI, is that sort of easy? Or?
Yeah. So this I didn't mention at all, but this is really in the last step. So remember that we're focusing on kind of the setting where the number of heads is small, because ultimately we depend exponentially on it anyways. So we might as well assume it's logarithmic in view of those cryptographic lower bounds. All right. So if you could estimate k, why is this useful? If you can get access to k exactly, then you can exactly access the subspace spanned by these M matrices. So that's step 5. And if you have the span, what you could do is simply epsilon net over the set of things in this span, this M-dimensional subspace, which are maybe a bounded norm, right? So I assume that these thetas had norm at most d to the m, but in general you could get an epsilon net that looks something like the norm bound divided by epsilon raised to the m. Okay, so it's going to be exponential in m, but the base of the exponent is depends on this norm bound in epsilon. Once you've constructed this epsilon net over possible parameters, then we use this kind of standard trick in the TCS or computational learning theory literature of just you can brute force search over all possible functions that you can assemble using some collection of theta i's. And for each one, I mean, once you have the theta i's, by the way, you can also finding the wi's just amounts to solving a linear regression problem, because wi is sitting outside of the softmax. Okay, so for any choice of parameters in this epsilon net, I could ask, is it actually close to the underlying function? And how do I do that? Well, I can just draw fresh samples and can sort of validate the test loss. Okay, so if the test loss is actually small, then I'm in good shape. Then I'm safe to output that choice of parameters. But you'll note that this, in that sense, we're not giving a full-on parameter estimation guarantee. We're kind of saying we output some, we're able to learn the span of the parameters, but we give no guarantees on whether or not the parameters that we found are close in parameter distance, only that they're close in test loss. But really,
so as long as you're happy with the f that is learned, I think that's a good guarantee, right?
Exactly.
So
yep.
Oh, okay. Does the audience have any more questions? Okay. If not, let's all just thank the speaker. Thank you so much for taking time out for us.
Yeah, of course.
And maybe then we can switch off the recording and take more questions offline.
Sounds good.